decades, returning rockets have faced the brutal thermal torture of atmospheric re-entry, suffering extreme heat, dynamic pressure, and rapid structural wear. Grid fins undergo intense mechanical stress while trying to steer massive metal tubes through dense, unpredictable air layers at hypersonic speeds. Traditional thermal tiles suffer severe degradation upon landing, requiring expensive inspections and lengthy repairs before the next orbital mission. Deceleration requires massive fuel reserves for retropropulsion, severely limiting the payload capacity that a launch vehicle can carry into orbit. Rough ocean landings on floating barges introduce highly corrosive saltwater exposure, which damages delicate electrical and mechanical booster components. Inside the main bridge, the crew of the Pride prepares to test a revolutionary magnetic levitation system to eliminate these harsh landing problems. Our starship navigates to the upper stratosphere, positioning itself perfectly to record this historic demonstration of next-generation physical engineering. A giant orbital recovery platform begins deploying massive electromagnetic copper coils, creating an invisible, powerful force field in the high atmosphere.
These massive coils generate highly controlled magnetic flux lines that act like an invisible soft cushion suspended high above the Earth's surface. Extremely cold liquid helium pumps through the system, lowering the temperature of the electromagnets to achieve perfect zero-resistance superconductivity. Deep inside the science lab, scientific telemetry confirms the magnetic grid is stable and fully operational for the incoming spacecraft recovery. Delicate instruments monitor the magnetic fields, ensuring the levitation cushion can dynamically adjust to the high velocity of the falling booster. Superconductivity enables the miraculous Meissner effect, causing magnetic fields to be entirely expelled and creating an incredibly strong repulsive force. Quantum locking pins the magnetic field lines inside the superconductor, locking the moving vehicle securely into a fixed, stable descent path. This advanced physics allows a heavy booster to be caught smoothly in mid-air without physically touching any solid, damaging landing structure. The massive receiving platform opens its wide capture ring, ready to receive the heavy orbital stage falling from the edge of space. The descending rocket activates its own onboard superconducting rings, preparing to match and interact with the platform's powerful magnetic fields. A bright blue glow emanates from the rocket's base as high-voltage power grids energize the heavy onboard magnetic deceleration phase. The Pride monitors the descent from a safe distance, capturing precise telemetry of the physics taking place during this high-speed return. Thick storm clouds part as the massive booster falls perfectly on target, guided by satellite navigation toward the center of the magnetic ring. Plunging through the thin stratosphere, the booster utilizes its aerodynamic shape to align perfectly with the invisible magnetic catching zone below. Air resistance creates high friction, but the booster maintains its steady orientation as it nears the powerful superconducting magnetic grid. Inside the main bridge, coordinates are updated in real time to synchronize the magnetic field intensity with the falling rocket's descent velocity. Telemetry displays show the speed decreasing rapidly as the opposing magnetic forces begin to interact, creating a safe, controlled deceleration cushion. Onboard superconducting arrays reach peak magnetic output, preparing to mesh with the ground-based magnetic fields in perfect physical alignment. The booster plunges directly into the magnetic field catcher, instantly generating an invisible, powerful braking force that slows its rapid fall. The flight crew monitors the intense energy exchange, watching as kinetic energy is safely converted into electricity without generating physical wear. Intense magnetic lines compress and warp, acting like highly elastic giant rubber bands that absorb the kinetic energy of the falling rocket. Eddy currents swirl across the receiver plates, generating a natural braking force that gently opposes the downward movement of the spacecraft. Giant superconducting energy storage capacitors absorb the massive electrical surges, capturing the energy of deceleration to power the next launch. The booster's speed drops to near zero as it hovers beautifully above the platform, completely suspended by invisible magnetic levitation force. This revolutionary technology allows the multi-ton vehicle to float weightlessly, eliminating the need for expensive, heavy landing gear and fuel.
Active magnetic feedback systems adjust the field strength microsecond by microsecond, keeping the floating booster perfectly balanced and centered. With the rocket completely stationary and levitating, mechanical docking clamps slowly extend to secure the pristine metal fuselage of the booster. The locking mechanism secures the base with a soft metallic clip, transferring the structural load gently from the magnetic field to the platform. The high-power superconducting coils slowly ramp down, transferring the vehicle weight entirely to the mechanical support structures of the base. Automated service arms immediately move in, connecting fuel lines to begin refueling the completely undamaged rocket for its next mission. Inside the lab, detailed structural scans confirm zero stress fractures and absolutely no thermal damage to the rocket's resilient outer hull. The heat shielding remains in perfect condition, demonstrating that magnetic recovery completely eliminates the structural stress of physical landings. By bypassing deep maintenance and refurbishment, the launch system can be ready to fly again in just a few short hours.
With the test successfully completed, the Pride prepares to chart its next course, having witnessed a monumental leap in spaceflight efficiency. Solar collectors on the platform open to recharge the superconducting coils, preparing the magnetic landing system for the next returning spaceship. This breakthrough opens the door to fully reusable orbital fleets, making space travel affordable, sustainable, and highly frequent for humanity. The crew gathers to celebrate their success, knowing that the era of throwaway rockets is officially over, replaced by clean magnetic technology. Looking forward, the future of deep space exploration is closer than ever, powered by the incredible power of superconductivity and magnetic levitation.